Okay, good afternoon. Thank you for the invitation. My name is Suyang. I'm from Professor Zahia Sang's group in the physics department of Princeton University. So today I'm going to tell you about our theory and experimental discovery of the first Weyl semimetal state and the associated topological Fermi arcs in this compound tantalum arsenide. Okay, let me start by thanking all the team members. So our RPS team at Princeton is led by Professor Zahia Sang, and then we collaborate with various groups for various projects. For this Weyl semimetal project, we mainly collaborate with Professor Jia's group in Peking University, and also with Professor Chou's group in Taiwan. And also, none of the works will be possible without all the helpful assistance at the beamlines all over the world. Okay, so topological insulators 3D was discovered in around 2007 and 8, and this is really well known now that on the surface it has this Dirac fermions, which are basically spin momentum locked Dirac particles. And now in quantum field theory, we know that there are another two types of fundamental fermions, massless. One is Majorana fermion, the other one is Weyl fermion. And then the two of the truly exciting new frontiers that emerge from topological insulators are to search for Majorana fermions and to search for Weyl fermions. And the first one is linked to find a topological superconductor, and the second one is linked to find a topological Weyl semimetal. So today I'm going to focus on the second part, about the Weyl part. So here I'm just listing some of the useful reviews. For topological insulators, there has been many, and then for Weyl semimetals, there has been only theory reviews. For example, here is a review by Wolfak and Vishwanath. Okay, so one slide about topological insulators. So this is, for example, the most well-known one, bismuth selenide and bismuth telluride. It has this spin momentum locking. And on the surface, it realizes a Barry phase of pi, and that corresponds to the invariant in the bulk, the mu naught equals 1. Yeah, so this has this metallic surface states on all surfaces. So one recent advance that I want to point out is that in collaboration with Professor Chen's group in Purdue, we now discovered a compound. This is bismuth, antimony, tellurium, selenium, and this compound, in contrast to the previous TIs, the difference is that now it's really bulk insulating, and the surface also has a high enough mobility so that we can see very well-defined plateaus that arise from the quantum Hall states from the topological surface states. So now this means that this sample BSTS is really in the topological transport regime, and one can really test the device applications for the 3D TIs using this sample. Okay, so now let's go to our topic. So we know that in topological insulators, it's defined by the topological number, like the mu naught Z2 number, and that number fundamentally requires the bulk has a full insulating gap. But then we want to ask the question, can metals also be topological? Know that in the metals, the bulk will not have a full gap. So then the question is that, how we define a topological number for a metal if it's topological, and what would be the surface states that corresponds to a topological metal? And it turns out that the answer is the so-called Weyl semimetal, where the quasi-particle excitations of the bulk obeys the Weyl equation. So Weyl fermions was proposed by gentleman Hermann Weyl in 1929, and what he discovered is that if you take the 4x4 Dirac equation and then take the mass term to 0, then it's sort of reduced to a 2x2 equation, which is what we so-called Weyl equation now. And then solving that Weyl equation will give you a 2x2 massless fermionic particle that has a definite chirality, either left hand or right hand, so that basically that is the Weyl fermion particle. So what I want to point out is Weyl fermions play a very important role in particle physics, like a standard model, but it has never been observed as a fundamental particle in particle physics. And therefore now the Weyl semimetals in condensed matter actually provide the first ever realization of Weyl fermions in all of physics. And it has many exciting properties that I don't have time to cover all of them, but I just want to highlight that in contrast to a topological insulator, where only the surface states, the Dirac surface states are a desired thing, are interesting, and one wants to get rid of the bulk. Here in a Weyl semimetal, both the surface and the bulk are interesting. So in the bulk, we have the Weyl fermions, and on the surface, there are these Fermi arc surface states. So therefore, this really opens up a whole lot of research opportunities for both bulk-sensitive probes in experiments such as transport, and also surface sensitive probes such as RPES and STM. Okay, so then the question is, we know that Weyl semimetals are very interesting, but then how do we find a Weyl semimetal? So this links back to an earlier work which we did, I think, in 2011, which is to realize a topological phase transition in a topological insulator, and that gives rise to the 3D Dirac semimetal. So basically what we know is if we take a 3D Dirac fermion, and if we, on a lattice, and if we break either inversion symmetry or time reversal symmetry of the system, then the Dirac node will split into a pair or multiple pairs of Weyl nodes that have, each pair has opposite chiralities. So that will give rise to a Weyl semimetal. So then in 2011, we have realized this topological phase transition from a 3D topological insulator to a trivial insulator. So this is done in this thallium bismuth selenium sulfur system by basically changing the composition of 100% selenium to 100% sulfur, and this effectively changed the spinor decoupling, and then at a critical composition, then the bond bands touch each other, form a 3D Dirac semimetal, and in this case it happens to be around 50-50%. Okay, so now if we take this critical composition and then this Dirac semimetal, and then if we really break the inversion symmetry or the time reversal symmetry of this thallium bismuth system, then we will get a Weyl semimetal state. But then at that time we found out that for this particular system, breaking either symmetry is experimentally very hard. So, but this at least demonstrate the spirit or the methodology. So then let me talk about some of the theoretical proposals before our work. So the first Weyl semimetal material proposal is done by Wan, Turner, Vishnov, and collaborators. This is in 2011. They found that in certain irradiate where there's, if they assume some sort of a magnetic ordering, then they predict that there will be a T-breaking Weyl semimetal phase. Similarly, later on that year, Burkhoff and Balance proposed that if you consider a superlattice consisting of multi-layers of topological insulators and normal insulators, where you have to fine-tune the parameter to the critical point and then develop a magnetic ordering, this will also give you a Weyl semimetal state. And later on the same year, I think this is from the IOP group, they proposed this is a stoichiometric compound mercury chromium selenide, and it is indeed a ferromagnet in experiment. And they propose that this can also give rise to a Weyl semimetal state. So we have tried these samples very extensively when they were proposed, especially this one where the mercury one where we can find large single crystals. I remember that my colleague and I used to keep a lot of samples at even one beam time, just try to see if we can see any RPES band structure that it's that will show the Weyl state, but we couldn't find anything that is close there. So later on, we realized that why that the T-breaking Weyl Semimetals are so hard. For example, for this mercury compound, this is a cubic compound. So that really means that in the magnetic phase, the A and B and C are equivalent. So then you would form many magnetic domains. And note that in R-phase you cannot add a magnetic field to align the magnetic domains. So then you have many domains, and then your R-phase spectrum will be averaged out. And the other problem is that in calculation, actually, the band crossing is between mercury s orbital and selenium p orbital. But then when you add a band gap correction, then the band inversion is actually removed. So similarly, the other two proposals have many, in the experiments they have many problems. For example, in the irradiated case, even the magnetic ordering itself they use in experiments is under debate. And then for the crystals are extremely small and they're hard to grow. And for the multi-layer case, obviously you require a very fine tuning to the critical point, and you also have to develop a magnetic ordering in these non-magnetic compounds, which are very hard. Okay, so then T-breaking is hard. Then we were wondering, what about breaking inversion symmetry? So I just want to point out that before our work, there was a proposal by the Vanderbilt's group. They proposed that in this rare earth, bismuth antimony tellurium compound, and if you sort of calculate the band structure, there's a very fine region between below 5% region. There will be a Weyl semimetal phase if they use a crystal structure that breaks inversion symmetry. But then what we found out is that the crystal structure they're using is actually hypothetic, and our sample growers told us that in reality it's extremely hard to actually grow the crystals in that desired crystal structure. That's one thing, and also this you see that it requires very fine tuning, only within 5%, it will have a very small region and will have a Weyl semimetal state. So this is hard. But then I want to point out a very completely unrelated but sort of another important fact. So here I'm pointing out a truly experimental data on immersion breaking single crystal. But this is nothing wild. This is just a trivial band insulator, bismuth tellurium iodide. But then it has this simple ABC stacking that breaks the inversion symmetry. So now here is the R-phase data, and we see this beautiful Rashba bands from the bog. And this is our data, but this sample is also studied by many other R-phase groups. And what this tells us, we know that the R-phase beam spot is quite large. And the fact that we see these beautiful bands, it must mean that the domain size of the inversion eye-breaking crystals, at least in certain cases, it can be large enough, and we don't have to align them by a magnetic field. They're just as grown, so then they're large enough so that the R-phase can be done. So now, to show that they're immersion breaking, obviously. So now, so this really, gives us a lot of confidence. Now that we know that the immersion breaking single crystals are more, feasible in experiments. Now we just need a robust candidate for Weyl semimetal. So then the question boils down to how do we find a immersion breaking Weyl semimetal candidate? And then if you look on the crystallographic library or database, you find that even for immersion breaking single crystals, there are so many. There are like tens of thousands of single crystals that are immersion breaking. So then we have to find out which ones are Weyl semimetal. So then we started to search that by ourselves, and then we developed a systematic methodology to look at all this large number of compounds to find out which ones are Weyl semimetals. And it turns out the first successful case was this tantalum arsenide 1,1 binary case. And we found that this is a immersion breaking Weyl semimetal, And our paper was submitted in 2014, November, and then was now published on Nature Communication this year. And it happens that around the similar time, the IOP group also found in theory that this tantalum arsenide is immersion breaking Weyl semimetal around a very similar time. What I want to say is because now we have this method to find immersion breaking Weyl semimetals, we have found many more. For example, one of the compounds that we made public is this strontium silicide, and we found that this is even more exciting because it has this quadratic Weyl fermions, which means that the Weyl fermions have quadratic dispersion and has a ±2 chiral charge, a higher chiral charge. And then we have found even more, and we're going to make them public soon. Okay, so here is just pointing out that this paper is now published and it was submitted in 2014. So now, okay, so let me talk about the theory part, PAS being a Weyl semimetal. So the crystal structure of tantalum arsenide is tetragonal, and then if you look along the 001 direction, each layer consists of only one type of atom, and they form a square lattice. But then they stack in a way that the crystal itself breaks inversion symmetry, as you can clearly see from this unit cell. And now, when you calculate the band structure, even along just simply along the high symmetry axis, you see that along this sigma and sigma 1, there is a quite robust band crossing between the conduction and valence band, about 0.5 dB. And then when you add spin-orbit coupling, you see that the band crossings are gapped out along the high symmetry axis. So now we need to find whether there are Weyl points or not. I just want to point out that without any special symmetry reasons, the Weyl points are usually not along any high symmetry axis or rotational axis, or not at any Kramer's point or high symmetry points. They're usually at some arbitrary points within the BZ. So that means we really have to calculate the band structure throughout the first Brillouin zone to find out whether there are Weyl nodes or not. So here is the answer for tantalum arsenide. Without spin-orbit coupling, as I mentioned, there's already band crossing along the high symmetry axis, and if we calculate the full BZ, we find that without spin-orbit coupling, the band crossings are actually one-dimensional. So that means the conduction band and valence band dip into each other, and they form this one-dimensional kind of like a ring-like touching. And in the first BZ, there are 4 of them. They're on the kx equals 0 and ky equals 0 middle planes. And then when I add the spin-orbit coupling, the nodal lines themselves are gapped out. But then if I go slightly away from the nodal lines, I find point-like touchings. And then if I count in total, there are 24 Weyl nodes. These are the Weyl nodes. And in total, there are 24 of them in tantalum arsenide. And so we name the Weyl nodes that are on this kz equals 2 pi nu plane as W1, and then there are 8 of them, and then the other 16 that are away from this plane as W2. Okay, so we can actually also calculate the distribution of the Berry flux, like in the vicinity of the 2 of the Weyl nodes. We see that one serves as they really behave like monopoles and anti-monopoles of the Berry flux. Okay, so now I just want to summarize all the important works, pioneer works in this subject. For the theoretical prediction, we have this is sorted in the order of the submission date. So in the theoretical prediction, our work was submitted in 2014 and then published in 2015, and then in the experimental, and then there's an IOP theory paper, and then in the RPES experimental work, our paper was now published in Science in July, and it was posted and submitted in February. And there are also later works, including our own group, which study either TAS or related compounds. Okay.